Welcome to the Ontario High School video podcast series on acid-base fundamentals. This is part 5, where we talk about finding the pH of an aqueous solution containing a weak base. So, welcome. We're going to look at a problem first where we'll determine the pH of an aniline solution. Aniline is C6H5NH2, and it's going to be 0.3 moles per liter in strength. And the Kb value, the equilibrium constant for this weak base, is 4.2 times 10 to the negative 10th. Now, the keys to solving this are the understanding that weak bases hydrolyze water in small amounts. So that's described by this equation. C6H5NH2 plus H2O yields C6H5NH3 plus OH minus. From a Bronsted-Lowry acid-base definition, the aniline C6H5NH2 is a proton acceptor, so it's the Bronsted-Lowry base, and water acts as an acid in this reaction. Bronsted-Lowry acid, it donates an H plus to the aniline. So because the result of the hydrolysis of the water is hydroxide ion in solution, if we find pOH first, then we can determine pH using the relationship that 14 minus the pOH will equal the pH. We go ahead and set up an ice chart that reflects this equilibrium situation. Our initial concentration of the aniline, the C6H5NH2, is 0.3 moles per liter. Again, water we get to ignore here because it's not a part of the equilibrium. And then our C6H5NH3 plus is 0, and our OH minus concentration also is 0 to start. We're going to do for our change minus X amount, which we'll need to solve for the aniline. The C6H5NH3 plus is a change of plus X as it is for the OH minus plus X. So at equilibrium, we'll have 0.3 moles per liter of aniline minus X, and then X amount of C6H5NH3 plus and OH minus. Our Kb expression then is the concentration of the C6H5NH3 plus times the concentration of hydroxide ion divided by the concentration of aniline, C6H5NH2, and we can simplify that to X times X divided by 0.3 minus X. Just a simplification of our Kb expression with the actual value plugged in, 4.2 times 10 to the negative 10th is equal to X squared divided by 0.3 minus X. Because the Kb value is very small, we want to see if we can simplify this expression further by dropping the X out from the 0.3 minus X part of the expression. And if we do this, it'll prevent us from needing to use a quadratic. So we take our 4.2 times 10 to the negative 10th, divide it by 0.3, multiply by 100, and we get 1.4 times 10 to the negative 7%. And again, I personally use a 1% rule, that if this value is less than 1%, we can simplify that expression by dropping the X out. So our 0.3 minus X is essentially equal to 0.3 moles per liter. Okay, we go ahead and solve for X, which is our concentration of hydroxide ion, by taking the square root of the product of the Kb value times 0.3. So the square root of the product of 4.2 times 10 to the negative 10th times 0.3 is equal to 1.1 times 10 to the negative 5th moles per liter of hydroxide ion. We can go ahead and fill out our table now. So our change in the molar concentration of aniline, the C6H5NH2, is we're going to minus 1.1 times 10 to the negative 5th moles per liter from that. And you'll notice that when you do this using significant figures, 0.3 minus 1.1 times 10 to the negative 5th leaves you with 0.3 moles per liter. The value of the C6H5NH3 plus and hydroxide ion concentrations are 1.1 times 10 to the negative 5th moles per liter at equilibrium. Since we know the value of the hydroxide ion concentration, OH minus, we can find the pOH because it's equal to the negative log of the hydroxide ion concentration. So the negative log of 1.1 times 10 to the negative 5th is equal to 4.959. Now, the three numbers past past the decimal place on the pOH reflect the three significant figures in our original molar concentration. Now that we have the pOH, we can find the pH, because we know that the pH plus the pOH will add to 14. So the pH would be equal to 14 minus the pOH, meaning 14 minus 4.959 gives us a pH of 9.041. This is a weak base, and remember that a pH above 7 is considered basic, a pH below 7 is considered acidic, a pH of 7 is considered neutral. So a pH of 9.041 would definitely reflect that this is a basic solution. Well, time for you to do a problem. So here's what I'd like you to do. Write this problem down and pause the podcast, solve it. When you're ready to check your solution against mine, resume the podcast and we'll see how you did. I'd like you to determine the pH of a 0.20 mole per liter hydrazine, which is a weak base solution. And hydrazine reacts with water in the following manner. N2H4 plus H2O will yield N2H5 plus OH minus. So here water acts as a Bronsted-Lowry acid, donating a proton, an H plus, to the Bronsted-Lowry base, hydrazine, N2H4. And our Kb value for this is 9.5 times 10 to the negative 7th. Welcome back. Let's see how you did here. We set up the ice chart first, so we have our molar concentration of hydrazine, N2H4 to start, 0.2 moles per liter. Our N2H5 plus is 0 to start, and our hydroxide ion we consider 0 to start as well. Our change is minus X for the hydrazine, plus X and plus X for the N2H5 plus and the hydroxide ions. And so at equilibrium we have 0.2 minus X for the hydrazine, X and X for the N2H5 plus and OH minus. Our Kb expression is equal to the concentrations of N2H5 plus times the concentration of OH minus divided by the concentration of N2H4. So it's equal to, as we use our equilibrium ice chart values, X times X over 0.2 minus X. And we simplify that to X squared over 0.20. Now, I'm not going to show you the calculation of the Kb divided by 0.2, but when your Kb value is to an order of magnitude of negative 7th divided by 0.2, you can pretty much assume that it's going to be much less than a 1% value. So I just went ahead and dropped the X out of there. If you're ever in doubt, please do the calculation. But in this case, based on our history of calculations, we should be pretty safe. So in solving for X, which our interest in X is for the hydroxide ion concentration, we take the square root of the product of Kb times the 0.20 is equal to X. And when we do that, we're going to get 4.4 times 10 to the negative 4th moles per liter of the hydroxide ion. As we continue to look at this slide, the square root of the product of Kb times 0.20, I did not substitute the number in for Kb, but you definitely would want 9.5 times 10 to the negative 7th times 0.20 there. When you do that, you'll get X. As you take the square root of that product, you'll get X, and the hydroxide ion concentration is 4.4 times 10 to the negative 4th moles per liter. We can go ahead and substitute those values in for X, the 4.4 times 10 to the negative 4th moles per liter. And so at equilibrium, our values for N2H4, the hydrazine, is 0.2 moles per liter. For N2H5 plus and hydroxide ion are 4.4 times 10 to the negative 4th moles per liter. And we can now calculate our pOH. It's the negative log of the hydroxide ion concentration, which is the negative log of 4.4 times 10 to the negative 4th moles per liter hydroxide ion, which gives us a pOH of 3.36. And our pH value then is equal to 14 minus the pOH. So 14 minus 3.36 gives us a pH of 10.64. How'd you do? If you did not get this answer, it would be a good idea to start from scratch, re-watch the first part of the podcast, and try this problem again without referring to what you've already seen of this problem, and see if you can get to the correct answer. That would be very helpful for you. Well, we are at the end of part 5. I want to leave you with a quote from the very interesting comedian and social commentator Dennis Miller. You know there is a problem with education system when you realize that out of the 3 R's, only one begins with an R. So I wish you well. Stay tuned for part 6. Thanks.